So today we are talking about variants of RMSProp and Adagrad with logarithmic regret bounds. This was published in ICML 2017. I'm Mahesh, and this was co-written with Matthias Hein, who's currently at Tübingen University. So the motivation behind this work was to use RMSProp, which was proposed in deep learning community, to online convex optimization. And also currently it has been the case that the algorithms which were designed for convex problems were used for training deep nets. However, the algorithms which were designed for strongly convex problems were never used to train deep nets. So we want to tackle on this problem. So some of our main contributions are: we proposed a variant of RMSprop which is designed for online convex problems, and we also showed that RMSprop and Adagrad are equivalent in a certain setting, which will be clear later in this talk. And our main algorithm is actually SC Adagrad, and the variant of it is actually SC RMSprop. Both of these algorithms achieve optimal regret bounds, which means they achieve logarithmic regret bounds for strongly convex problems. And we show that these algorithms can actually achieve a better test accuracy on various deep nets. So let's consider the online convex optimization setting. So we have a convex set C, and we want to run the algorithm for t rounds. So in every round we predict an action which is essentially a point from the convex set C. You can think of it like weights of your model. And the adversary, so we are playing a game against the adversary. So the adversary chooses a function which is a continuous convex loss function. You can think of it like obtaining a sample from the training data set. And in each round you suffer ft of theta t loss. And using the subgradient information, we want to update our theta t, which is we want to update our weights using the subgradient information. So before going into the algorithm itself, we want to see the basic measures in online convex optimization. So one measure is the cumulative loss, which is just accumulating all the losses we have seen until capital T number of iterations or rounds. So, and also the best possible prediction in hindsight is defined to be something like this, which essentially means what would be the best possible prediction we could have taken for all the rounds combined to achieve the minimum loss. But note that this best possible prediction is constant in all rounds, and it is possible to achieve even lower than this by having a best possible prediction in each round, but we are not interested in that because it is too restrictive. However, by considering such a measure, which is just we are considering the best possible prediction in hindsight, we can hope to achieve an algorithm which we can compare against the best possible prediction in hindsight. So the adversarial regret would be just the difference between our loss, which is our cumulative loss till capital number of iterations, minus what the best possible prediction in hindsight would have achieved. So our goal is to bound the regret, which is R of t, and this entity depends on theta star, which we are not aware of. So that it makes this makes it a bit trickier. So there are many algorithms which were proposed to tackle this problem. One of the important and the initial algorithms which was proposed was the online projected gradient descent, and this was designed for convex problems. And they show that Zinkovic in 2003 show that by having a step size decaying as 1 over root t, we can have the regret O of square root t, which is the optimal regret bound for convex optimization problems. And there was a variant which was proposed by Ducci and all in 2011, which it's called Adagrad, which essentially uses the same idea. However, it, instead of depending on t, it rather tries to obtain a data dependent, which is it depends on the previous gradients and the current gradient in order to set the step size. And on the contrary, for strongly convex problems, it was shown in 2007 by Hassan et al. By having a step size decaying as 1 over t, we can achieve actually logarithmic regret bounds for strongly convex problems. And um, similarly, like what Ducci and all it did using a data dependent step size, we try to design a scheme where we come up with an algorithm which is entirely data dependent, and however it must achieve logarithmic regret bounds. So to that regard, we proposed SC Adagrad and SC RMSProp, and also we realized that um, by converting the RMSProp algorithm, which was proposed in deep learning, to online convex optimization setting, we had we came up with a new algorithm. So this algorithm actually achieves optimal regret bounds for convex optimization problems. So the analog for the strong convex optimization setting is SCRMS-Pro. So let's briefly revise the notation. So here A is a symmetric positive definite matrix, and we want to see what would be the weighted projection of vector Z onto a convex set C, which means essentially the norm you are considering is actually with respect to A. So essentially the norm is defined as this entity. So we denote the weighted projection with respect to A onto the convex set C as this notation, which essentially means that you are minimizing this particular optimization problem. And this symbol denotes element-wise operation. So this is AI, BI for each of the index. And the bold 0 actually belongs to the d-dimensional real space. It's a zero vector. So let's consider Adagrad versus SC Adagrad. So the basic idea behind Adagrad is to use the geometry of the problem in order to take the step size. So earlier in online projected gradient descent, the step size has to follow 1 over square root t decay in order to obtain optimal regret bounds for convex problems. Essentially to obtain square root t. Let's consider Adagrad versus SC Adagrad. So the basic idea behind Adagrad is to use the geometry of the problem. So in online projected gradient descent, we used step size scheme of 1 over root t in order to obtain square root t type optimal regret bounds. So we want to achieve the same optimal regret bounds using the data, which are essentially the gradients which we have seen in the past and the current gradient. So we accumulate the information from the previous gradients in order to take the step at the current round. So, and how we do this? So we essentially accumulate like a second order term and design a matrix AT such that we have effectively a different step size for each dimension. And this in a sense has an effective step size as 1 over root t after a bit of calculations, and then you can actually deduce that we can achieve a square root t type regret bounds for convex problems. This was proposed in Ducci et al. In 2010, and this is one of the most popular algorithms to train deep nets, and usually delta is chosen to be in 10 power minus 8, which is a numerical stability parameter. So in each round you essentially have the gradient information, and then you accumulate the second order terms, and then you have a square root t term. That's where the root t kicks in. So in essence you have an effective step size of 1 over root t. So an analog of Adagrad is what we propose, which is SC Adagrad, which we propose it for strongly convex problems. So online projected gradient descent has an effective step size of online projected gradient descent has step size of 1 over t, on the order of 1 over t in order to obtain the optimal regret bounds. So how would we tweak Adagrad in order to obtain the logarithmic regret bounds? So we have two main differences between Adagrad and Adagrad. One is the square root vt term goes away, and so the square root doesn't appear over here, and we have a numerical stability parameter delta t, which is constant in actually Adagrad, but we have the flexibility to choose to vary with round. But we have a mild condition on the way it can vary, which is delta t has to be monotonically decreasing element wise. So delta t can actually be a vector. So the constant delta scheme, which is if you use a constant numerical stability scheme, you you can indeed achieve logarithmic type regret bounds. This was proposed in 2010. So we want to see whether we can achieve optimal regret bounds by using such a delta t. And we show that we can actually indeed achieve a better test accuracy on deep nets. And we also propose a scheme for delta t where we vary the delta t according to the vt term. In that sense, the numerical stability itself is very adaptive. So let's revise what a strongly convex function is. We say that a function is strongly convex if there exists a lower bound. So more precisely, you take any 2 points in the convex set C, and we say the function is zeta strongly convex if there exists a zeta which is greater than 0, such that you have such a lower bound. So that the entire function is upper bounded by a lower bound which is constructed at x. So this is our main result of the paper. So the main theorem is that we are obtaining strongly convex functions in each round, and we obtain also the subgradient, and we need a behavior on the subgradient information. So we enforce this kind of bond on the subgradient, which means the infinity norm of subgradient is actually bounded for all the rounds. And here the infinity norm of the action minus the best possible action in hindsight is actually bounded. So this particular condition is usually written in a different way, where you can have a like a bounded set, and this is known as the diameter of the set. But this is a bit weaker condition because we are actually considering the distance between action and the best possible action only, and we don't need to consider other points in the set. And by choosing an appropriate step size, we actually have the following regret bound. Even though it may look a bit cumbersome, the basic idea is that you have a logarithmic term, and whatever you have inside, it is entirely data dependent, and it actually, once you upper bound it even further, you get it to be order of logarithmic t, which is optimal for strongly convex problems. Now we consider the different part of the talk, which is to convert RMSProp algorithm, which was proposed for deep learning, into online convex optimization setting. So the basic idea behind RMSProp was to use a moving average for second order gradient term, which we had for Adagrad. So if you remember from Adagrad, there was exactly the same kind of algorithm, but the Vt was just Vt minus 1 plus this particular term. But here we have a moving average term beta t and 1 minus beta t in order to appropriately tune how much we would be weighing the current gradient information, the second order gradient information here. And we also have a varying numerical stability scheme, and we need such a step size which is alpha by root t in order to compensate for the decaying scheme we had for the moving average. So in essence, like with this algorithm, you can get an effective step size as 1 over root t and get optimal regret bounds. which is you can achieve square root t type regret bounds for convex problems. And we also can see that if you ignore such kind of varying schemes for epsilon t and alpha t, and you set them to be constant, and you choose beta t to be constant, which is 0.9, then we obtain the original RMSProp. And now on the contrast, for strongly convex problems, we propose SCRMSProp, where we have exactly the same moving average gradient information here, which is Vt similar to RMSProp Rs. And similar to SC Adagrad, we remove the square root t term here in order to obtain AT matrix here. And here the numerical stability parameter scheme is exactly like SC Adagrad effectively once you cancel out the terms over here. So we have this condition that the numerical stability scheme has to be monotonically decreasing. And the effective step size we obtain is 1 over t, and thus we obtain logarithmic type regret bounds for strongly convex problems, and we also show that indeed it is data dependent logarithmic type regret bounds. And we observe an interesting phenomena where by choosing an appropriate value for beta t, we can have an equivalence between RMSProp and Adagrad. So we choose beta t equal to 1 minus 1 over t, and we have exactly the update steps what we have for Adagrad, and we get the same with RMSProp Rs as well. And similarly, with SCRMSProp, we can obtain as a special case SC Adagrad. So we propose a decaying scheme which is exponentially decaying with Vt, and we have two hyperparameters over here. So this is indeed a very good numerical stability scheme, because when Vt is large, then it's not required to have a big numerical stability parameter. So here it's good to have a decaying scheme with respect to Vt. And similarly for SCRMSProp, in order to compensate with the moving average term, you must have t times Vt. So what we achieve by having such a decay scheme is that we have this enhanced adaptivity, because delta t itself is a vector now. And also it stabilizes the quadratic growth of Vt in Gt. So what we mean by this is that let's consider a one-dimensional setting, and then we would be, if you consider the update step of SC Adagrad, we would essentially have Gt by Gt square plus the decay scheme. Let's say if you set the decay scheme to 0, then what happens is that you have this 1 over Gt dependency. If Gt was small, then the whole update step blows up. So by having such a decay scheme, it essentially blocks such a blowing up behavior. We go through in detail in the paper on this particular phenomena, and since this is exponentially decaying in Vt, it's not necessary to have like a very huge numerical stability parameter when Vt is large. In that sense, it automatically tunes the numerical stability according to Vt. And we found that these particular parameters really work for convex and deep learning problems here. But we couldn't solve the question of what's the optimal decay scheme. So now let's see some experiments. Let's consider the experimental setup. So we compare over SGD, Adagrad, RMSProp, and RMSProp Rs, SCRMSProp, and SC Adagrad. And we use 1 over t kind of step size decay for SGD, which is online projected gradient descent for strongly convex problems. And for Adam, we use 1 over root t step size, which is what they have proposed in the paper. And we use Adagrad and RMSProp with the numerical stability parameter set to 10 power minus 8. Actually, in all the algorithms, we set the numerical stability parameter to be 10 power minus 8. However, for SCRMSProp, we use such a kind of numerical stability scheme. And similarly, for SC Adagrad, we have such a scheme. And we use the step size from we use actually the best performing step size individually for each of these algorithms from the following set, so that the comparison is fair. And in the online L2 softmax regression setting, we see that SC Adagrad indeed achieves a lower regret value, and RMSProp performance, the original RMSProp performance is actually not so good over here. And similarly, we consider the test accuracy versus the number of epochs for a 4-layer CNN on Cypher10 and MNIST datasets. And here RMSProp Rs and SC Adagrad is really competitive, and here SGD performs really well, but SC Adagrad and SC RMSProp also catch up, but RMSProp original was not so good here. So SC Adagrad is actually competitive on both Cypher10 and MNIST. And we also consider the experiment where we consider the Resonate 8 architecture on Cypher10 dataset. And if we consider the training objective, here the RMSProp Rs and Adagrad are actually very competitive, and they are the best performing algorithms, and followed by SC Adagrad and SC RMSProp. And similarly, on the test accuracy side, actually SC Adagrad performs really well. So we have a high test accuracy on Cypher10 dataset by SC Adagrad. We have more experiments in our paper on convex problems and multi-layer perceptron. So the conclusion is that SC Adagrad is somehow very competitive on deep nets, but we do not answer the question why it works for deep learning, which is an interesting open question to answer. And I have the implementation for SC Adagrad and the other algorithms at this URL. You can ignore this line. And thanks for listening. These are some of the references.